right, so we're talking about logarithms. So we had something like y equals 2 to the x. And basically what I want to talk about is a different problem than what we were asking before. So now I'm going to talk about the situation where I'm going to put here's a formula we were just talking about, right? Where here I'm going to put 15,000. The problem we had before was to put 15,000 into an account at interest rate 5, compounded, let's say monthly, for 3 years, right? And for the moment, I'm going to take out this 3 and just say that for T years. So if my wife says, okay, let's put this money into this account, how much are we going to have? You're the mathematician guy, she would say to me. How much am I going to have after 15 years? And I would take 15 and plug it in here. And then she would say, well, how much are we going to have after 10 years? I would take 10 and plug it in here. When are we going to have $30,000? That's not the same question. When she says, how much am I going to have, that's a question about A. She gives me T, she gives me the time, and then I can give her the amount. And now she's giving me the amount, and I need to give her the time. So that is the inverse question. That's the inverse question. Any questions about that? Go ahead.
Still 4.1.
This is 4.2 now.
Okay.
This is 4.2. Logarithm is 4.2. So now it's the inverse question. She gives me the amount. She's like, yo, I want to pay for our daughter's college. We need $32,000. How long is that going to take? And my goodness, that's a legitimate question, right? That's a legitimate question to ask. And so the question is, how is it that we're going to solve for T? How are we going to get T by itself? Up until this point, if you're living only in the college algebra world or in the algebra 2 world, we actually may not know how to do that, right? So that if I have 3 to the x equals 15, the question is, what's x? How do we get x by itself? Okay. And so that's why we need to introduce a new function that's going to allow us to get x by itself. And that gives rise to what logarithms are. Okay. And so when we do 2 to the x, then we have something like this, right? We know this, right? If I have x and 2 to the x, right? Then when I plug in 1, I get 2. When I plug in 0, 2 to the 0 is 1. When I plug in 2, I get 2 to the second, which is 4. Negative 1, 2 to the negative 1, again, is 1 over 2. And negative 2 is 2 to the negative 2, which is 1 over 2 squared, which is 1 over 4. Right? That was the original function, 2 to the x. Now, I didn't use the term inverse question just by accident. Inverse is a mathematical term. Finding the inverse function. The street version of finding the inverse, what do you need to do to the x and y coordinates? You need to switch them. I need to switch them, right? So that 2 to the x has an inverse because it's increasing. And so now I want to look at the inverse of 2 to the x. Just simply means, which for the moment I'm going to call I. Here's the inverse, right? And all I'm going to do, so that's a function. The inverse, all you're going to do is switch the x's and y's. We're just going to switch the x's and y's. And so if I plug in 2 to the inverse, what should you get? 1, for sure. 1 goes to 0, 4 goes to 2, 1/2 goes to negative 1, and 1/4 goes to negative 2. The inverse, you just switch the x's and y's. I'm about to introduce some notation. This notation has scared many people over the 20 years of teaching I've had, right? But what I want us to do is try to understand what we're saying, okay? So I'm going to put 8. We didn't do 8. But if I did put 8 here, what would 8 go to? No. What's 8? Eight would be 3. Why?
Because it's 2 to the 3 is 8.
Because 2 to the 3rd is 8. Is that okay? When I put in 8, I get 3 because 2 to the 3rd is 8. Questions on that? Go ahead.
So that's still applying to the ones above it.
Wait, what do you mean? That's for all of these. That's right.
Okay.
I get a 2 because 2 to the 2nd is 4. Right? 1/2 goes to -1 because 2 to the -1 is 1/2. That's right. Right? So that the numbers over here give you what? We'll say it in just a second. It gives you the power. So this here gives you the power you need to raise 2 to in order to get this. Right? So then if I put in 16, this would be 4, because 4 is the power you need to raise 2 to in order to get 16. The inverse gives you the power you need in order to get this. Go ahead.
So referring to 2 for all these,
Yes.
would that be the same for 3, 4, 5, 6?
We're about to, of course, generalize in just a moment. Right now we're talking about 2. That's right. The questions about this, about why this is 4, is simply the power you need to raise 2 to in order to get 16. You know what I'm about to do. 37. 37. That's kind of rough, but sure it is, right? First of all, we know, let's just verify, we know that 37 has a number, right? If I go back here, 37, let's bring this one back. Turn that one off. Y equals 37. Let's see, oh, maybe not. Oh, there it is. It's there.
Between 5 and 6.
Yeah, roughly between 5 and 6. At 5, 2 to the 5th is 32. 2 to the 6th is 64. Whatever this is, it's between 5 and 6. Right? But it's there.
Yep.
We just need to give it a name. We just need to give it a name. Right, now, whatever name I give it, what 2 numbers should it probably involve?
2.
2 and 37. Right? 2 and 37.
Yep.
I need the number that I will raise 2 to in order to get 37. Here's the name I'm going to give it. It's that. That's the name. That's the name. However bad it looks, all that is the power you would raise 2 to in order to get 37. It's there. It's ugly. It's irrational. Right? That's actually a mathematical term. Irrational means that if you write out all the decimals, right, it goes on forever without repeating in any way. We do not know the 500 millionth decimal place of this number, because nobody really cares, right? But we also don't know it. Go ahead.
I don't understand why you use a graph with 5 and like the discrepancies.
Say that again. So this,
you said it was like between 5 and 6.
yeah, that's right. So at 5, the answer 2 to the 5th is 32. 2 to the 6th is 64. So whatever the number is going to be is between 5 and 6. That's all we're saying. The x value, so this value here is 5, and I think this one's 6, right? And so the answer is somewhere in between. There's the decimal approximation. We were just suggesting that if you wanted to estimate it, that because we know that 2 to the 5th is 32, which is less than 37, and 2 to the 6th is 64, which is more than 37, then the actual answer is somewhere between 5 and 6. Yeah, thank you for that. So there's the decimal approximation. Of course, people have done all the work to make nice calculator approximations to this, right? That is not the exact answer, right? The exact answer is log base 2 of 37. Okay. It's the unique number that solves this. Excellent. Sounds like time for a definition. Here's the definition. When we write y equals log base b of x, first of all, again, we're going to need b to be greater than 0. There's no point in having a base of 1. And we're going to see that x needs to be greater than 0. We'll explain why that needs to be true. We know what this means. When y equals log base b of x, all we're going to say is that this means that y is the power that you raise b to in order to get x. That b to the y power is equal to x. Means exactly the same thing. So this is log form, and this is exponential form. The log is the power. Give me one moment. The log is the power. That's the lesson for section 4.2. The logarithm is the power. Go ahead.
Every point chapter we go through when I have homework section.
Yeah. I'm doing homework for each one. Yeah. The log is the power. The log is also the inverse of the exponential. It's also the inverse of the exponential. Right, so f of x equal to b to the x and g of x equal to log base b of x are inverses.
That's not supposed to be anything in front of b, right?
It is not.
Okay.
I was going to be lazy and just leave it.
Thank you.
Oh, no. Thank you for keeping me in check. They're inverses. So I've introduced a new function. Of course, we need to talk about the domain and the range. Let's go ahead and plot this one. I had 2 to the x. It's not going to be so shocking what the inverse looks like. I'm going to have to reflect 2 to the x over what line? Remember? They're inverses. Log base 2 of x. There it is right there. Let's see. We can make it nice. There we go. All right. So if we're switching the x and y coordinates, oh no, don't move, don't move, you stay there. That's the line y equals x. There's reflections. When functions are inverses, then one graph is just a reflection of the other graph over the line y equals x. Right? So it's not so shocking that if at 0 you get 1, right? So 0, 1 is on one graph. What point do you think is on the other graph? 1, 0 for sure. I mean, you plot them all, it's just a reflection over that. And so just as we would expect, at 2 you get 4 for the inverse, at 4 you get 2. Just switch the x's and y's. Questions there? So I brought this up only because now looking at the graph, it informs us as to what the domain and the range are. So, but we know, because we know the domain and range of the exponential function, all we need to do is switch them for the inverse. If the domain of the exponential function was the whole real line, right, that is to say that the red graph moves all the way to the left and all the way to the right, then the purple graph should move all the way down, all the way up. Right? That if the domain of the red graph is minus infinity to infinity, then the range of the purple graph minus infinity to infinity. Whatever the x's we're doing for the original function, the y value is going to be doing that for the inverse. You just switch them. So to say that, by writing it, the domain of log base b of x is the range of b to the x, but the range of b to the x was 0 to infinity. The range of log base b of x, it goes all the way up and all the way down. You don't go to the left of 0 for the log graph, but you go all the way to the right, and the log graph goes all the way down to minus infinity. And although it's not convincing, that thing goes all the way up to infinity. Now the great skeptic will come in and say, I don't believe you, right? And I have to convince the great skeptic that that's true. Go ahead.
So domain and range just reflect each other?
For the log versus the exponential, that's right. Because all we're doing is switching the x's and y's. Yeah. That is right. All right, so that talks about the functions, right? So, so the great skeptic is going to come in and say, look, let's turn this one off. Let's turn this one off. You're trying to convince me that this thing goes up to infinity? So in terms of calculus, this is going, so first of all, the exponential is going to be our fastest growing function. That thing goes up so fast. Its inverse is going to go up so slowly. Look how slow it's going up, right? Let's see just by looking at a few of them. We'll need some notation. Some special logs, the common logarithm uses a base that we're all used to, and it's base 10. And we're going to write it without the 10. If you just see the log of x, then the base is 10. The base is 10. We love base 10, particularly my people in chemistry, astrophysics. We use scientific notation. Everything's 3 times 10 to the x. Avogadro's number, 6 times 2.3, 6.23 times 10 to the negative 23rd. Right? The mass of Jupiter is 10 times whatever, 10 to the 400th times the mass of Earth, right? So powers of 10 are so huge that, you know, if we're using base 10, you're just going to say that's just log. There's another number that we really care about, and that number is e. And so when the base is e, we can talk about why e is important in calculus in a moment. We like it so much, we call it natural. It's the natural log. All right, so we write ln when the base is e. The log is the power. The log is the power. We'll start looking at some values in the domain in just a second. So this is called the natural logarithm. Natural. We like the base e, and we call it natural because it has a property that other logs don't have. Right? So when I write e to the x, and I write 3 to the x, right? And I put back 2 to the x, then I go back to the origin. Let's just go back home, right? So they're all intersecting in certain ways, right? And we can see that the highest one needs to be the one with the largest base. The one with the bigger base obviously increases the most. Powers of 3 are bigger than powers of 2. E is a number between 2 and 3, so it's the one in the middle. Right? E is 2.71828, blah, 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 blah. Why we can like this one better is because at 1, this is a calculus thing about how things change. At 1, the slope is at 1. The slope is 1 for E and for no other base. It's simply because when you look at the slope at 1, it's 1. It's the only number where you make that the base for exponential functions where the slope at 0 is equal to 1. Right? And so that makes formulas really nice when you do calculus stuff. You'll see that for my people going into calculus, that when the base is E, it makes things much nicer when you're doing calculus things. Okay. So that's why we like E. right? And in my math lab, they'll want you to use, I think they've changed it. Usually in my math lab, they only want you to use the natural log to solve these things. But I've seen some of these problems and they'll let you use the natural log or the common one. So I think they've opened their mind. Right? This does bring up a question though about, it seems like we have all these bases. What happens if you're doing your work and you love base 3, someone else is in computer science, they love base 2, how would you ever talk? If you like one base, someone else likes a different base, right? How is it that we can go from one base to the other? Why is it that when you look at your calculator, it looks like they have the log base, they have the common base, they have the natural log base. Where's base 15? Why is base 15 not on your calculator? Right? I have to answer that question too. Okay. All right, let's look at some values. The log is the power. The log is the power. What's log base 3 of 9?
Two.
It's 2. Why?
3 times 3.
Because 2 is the
Power.
power you raise 3 to in order to get 9. Right? It's 2 because 3 to the second power is 9. The log of something is just the power. Please.
Is there like some practice question for that? Like the Pearson or something?
Yes, we're going to do the homework in just a second. Yeah, absolutely. Log base 4 of 64. 4 to the 4th is not 64. 4 to the 4 to the 8th. 4 times 4 times 4 times 4 times 4 times 4 to the 3rd is 64. It's 3. Because 4 to the 3rd is 64. The log is the power. Log of 100. 10 to the 10th? Is 10 to the 10th 100? 10 to the 2nd. 10 to the 2nd. Right? So this is because my eraser police are going to make me erase this. So I'm going to do that. This is equal to log base 10 of 100. Right? I didn't write what the base was, so it was 10. And so 10 to the 2nd is 100. Okay. Questions there? Log base 10 of 1 million. How many zeros are we talking about? 6 for sure. And so this is why the skeptic keeps knocking on my door and saying, wait, you think this goes to infinity? If I go on the x-axis, 1 million feet down the x-axis, this thing only hits 6. If I go a trillion ways down the x-axis, I'll be at 12. And you want me to think this thing goes all the way up to infinity. And we say, yes, it does. It will just take forever. It'll take so long. As fast as it takes the exponential to go up, that's how slow it takes the log to go up, right? It's just the inverse, right? The proof of that is due to Weierstrass, where he was able to put all this stuff in hard mathematical terms for me to show that the log goes up faster than anything else. The one application of logs is simply based on this, right? That at this point, at least it used to be true 2 decades ago, that when you're dealing with stuff like astrophysics, that or stuff like chemistry, where you're dealing with very, very large things or very, very small things, it would be very hard to do arithmetic on these things, particularly if you're computing stuff. When we're talking about Avogadro's number, you're talking about something of the order 10 to the minus 23. You're talking about something that's 0 to 23 decimal places. And then you want to add, multiply, divide, right? So if you take something that's 0 to 23 decimal places and multiply it times something else, for most computers, they're just going to give you back 0, right? Because it's all floating point. I got IT people in here. You all know this, right? That you got something that's 0 to so many decimal places. The programmer is just going to call that 0 just to save all space and all this other stuff, right? However, if you apply the log to it, then you get a number that's manageable. Right? When you're talking about the mass of Jupiter, right, and it's so large that if you do arithmetic on it, that your computer can't handle it. If you apply the log to it, it becomes something that's manageable. Then you can do arithmetic on that, and then take the inverse and see what you can get and do some analysis, right? So that logs are helpful in handling large numbers. They make large numbers controllable. It turns 1,000,000 into 6. Right? It turns 10 to the 23rd into 23, and then you can do something with that, right? So you'll see people work on log scale, right? When you're in physics, or if you're in psychology, even people are working on log scale, where they've taken the log of the axis, they've taken the log of the y-axis, and then so to find the correlation between two variables, x and y, and those two variables are completely unmanageable, they take the log of both of them and then look at that relationship. And it's going to be the same relationship, right? But it's just that you couldn't do any arithmetic when the numbers are too big. Right? One other application is, my cousin lives in California, and so he'll talk about, earthquakes that will happen, right? And I'll hear this on the news that last week, there was some earthquake in California that was 4.1 on the Richter scale, right? So it's 4 on the Richter scale, and then the very next week, and then they'll say, oh, and that won't even be on the news, but he'll call me and he'll say, yeah, we had an earthquake, it was 4 on the Richter scale, and then 2 weeks later, there'll be a 6 on the Richter scale, and then he won't call and tell me that, but I would hear that on the news. Somehow 6 on the Richter scale is way worse than 4 on the Richter scale, and it's because they're using the scale as a logarithmic scale. Okay, so that they're saying that, let's suppose that the base is 10. It doesn't really matter. They're saying that log base 10 of some number is 4. Right? That's 1 week. Right? And then they'll say 2 weeks later that log base 10 of y is 6. Well, we know what this means by definition. When I write log base 10 of x equals 4, this means what? 10 to the 4th power equals x. X is 10 to the 4th. What does this mean? Y is equal to 10 to the 6 for sure, right? So then it becomes pretty clear why it's different. That this force of nature that is an earthquake that shakes the very ground, right? When it's at a 4, my cousin may be walking along and it's just like a little tremor, right? But that's, what is that, 4 zeros? What is that? 10,000?
Yes.
That's 10,000?
Yes.
What's this?
1,000,000.
1,000,000. Whatever this is 100 times that. It's 100 times that. Right? So that what was once like some little tremor, when you multiply by a factor of 100, then you expect stadiums to crumble. Right? In '89 in Oakland during the World Series, they had an earthquake, shook the whole place. Right? Right? So that, again, so when you hear about the Richter scale, it's a clear application of logs, right? Whatever the base is. That 6, 8, you'll never see an earthquake that's 8 on the Richter scale. It would drop an entire state, right? It's because it would be 10,000 times as big, right? It's just something ridiculous like that. Okay. All right. Domain, range, application, homework in a second. Make a few more comments. Log base 4 of 1. 4 to what power is 1? 0. 4 to the 0 is 1. We'll make the remark this has nothing to do with 4. Log base 7 of 1? 0. Log base 11 of 1? 0. Log base b of 1? 0 for any base. The log of 1 is always 0. Log base 3 of 3? 1. 3 to the first is 3. Log base 9 of 9? 1. Log base b of b, 1. For any base. Because 3 to the first is 3, 9 to the first is 9, b to the first is b. Log base 7 of 700, log base 7 is 7 to the 403 power. 403. Right? It's the power you need to raise 7 to get 7 to the 403. We certainly wouldn't multiply this 7 times. I mean, 403 times, right? This is just the power, right? So again, the other way to explain this is that, again, these are inverses. So they should just cancel each other out. They just cancel each other out and you get the power. Of course, that has nothing to do with 7 or 403. In general, log base b of b to the u power is just, I'm sorry, of b to the u power, oh no, is u for sure. Let's get the eraser out. B to the u is u. Right? Again, because they cancel. Going the other way, 3 to the log base 3 of 17 is 17. That's by the definition. That log base 3 of 17 is the only power that if you raise 3 to it, you would get 17. So that now I'm raising 3 to it. I better get 17. Because this serves the very purpose that when you raise 3 to this thing, you're supposed to get 17. So 3 to it is 17. The other way that you explain it again is that these just cancel. They are inverses. 3 and log base 3 are inverses. They cancel. You're left with 17.
Can you put the second one?
Say it again? Where?
The second one.
Here or did you?
After D0.
This one?
Or log 3 equals 1.
This here. Thank you. So the log is the, what's the log? This is good. The log is the power. So when I write log base 3 of 3, I'm looking for an exponent, right? I'm looking for the power I need to raise 3 to in order to get 3. And 3 to the first is 3. That's why it's 1. Okay. The log is the power. And this is what I mean about just remembering. So again, this is the mathematician in me. That I'm never going to talk about something unless it has a clear definition and I talk about a street version of it, right? So whenever I introduce something, in order for you to make it you need to make it make sense to yourself. I offer a street version, maybe that's the way, but you need to think about it however you need to think about it so that it makes sense to you, right? But whenever you see something, you have to say to yourself, well, wait, what does that mean again? And if you remember that it's the power, a lot of this stuff comes pretty straightforwardly. I think we're ready to hit the homework here. This is in logarithmic form. We want to write it in exponential form. In other words, they just want you to apply the definition. 4 is log base 5 of 625. This means that 5 to the 4th is 625. That's what they want you to write. 5 to the 4th equals 625. That's the answer. It seems like they have a particular way they want you to put this one in. The exponential form, we know it's b to the 2nd equals 81. Which side are we supposed to write which side on? So type the expression containing b or y on the left-hand side. So they want b to the 2nd on this side. B to the 2nd power equals 81. B to the 2nd power equals 81. And again, all you're doing is starting at the base, raising it to that power, and it needs to be equal to that. That's a fact. 6 to the 3rd is 216. If you're writing that in logarithmic form, I need to write it as log base something of something equals something else. We know that the log is the power. The power should go there. Here, the base should go there, and the rest should go there.
So
right? Log base 6 of 216 equals 3, right? And of course you can just test it, right? Because 6 to the third equals 216. So that's what we were right here, right? Log base 6 of 216 equals 3.
So I want to be clear. We are going through these log rules because we still want to answer my wife's question. How long is it going to take for us to have 32,000? Right? So, you know, we have this new inverse function. We're going to look at all of its properties. It has one particular nice property that's going to help us solve that question, right? But we need to get there. Okay, so right now we're just dealing with all these properties of logs, and then eventually we're going to use the log in order to solve that equation and answer a question about how much time it's going to take.
Same thing.
Try and write that one in log form.
Log base blank of blank equals blank. 6 x 94. Questions?
Most of you have used my math lab before. So the subscript, you can just do shift minus sign, gives you a subscript. They have a button at the bottom too, you can press for subscript.
You want to tell me about board 2.17?
Say it again? Oh yeah, sure. So yeah, I've decided to add in the ID number. So, you know, if you need to practice this, you can go to the study plan. If you go into the study plan for each section, you click on the section in my math lab, and then you click on 4.2.17, and you can practice these as much as you want. Right, so that's what the ID number means.
Number 5 is another one that you can answer. That's very much the same thing.
I have a question.
Please.
Can you switch the 6 in place of, so it doesn't matter order, whichever side is on the equal side?
Well, you can put the 6 here.
Okay, and then put the log on the other side.
So you could put, you could put the 6 here and the log on the other. You could write 6 equals. Yeah. You could have written 6 equals log base x. Yeah. Yeah, and my math lab should take either one.
So right, so this one I could have written that a equals log base 7 of 225, right? I could have written that.
Yeah.
And then we're going to roll through these. Log base 7 of 49. 2. Questions? What power do I raise 7 to get 1 over 7? Right, there's that negative stuff again, right? So 7 to the negative 1 is 1 over 7. What power is the square root? 1/2, right? So the square root of x is just x to the 1/2 power, right? So they're being nice, but log base 4 of 2 is 1/2.
The square root is the 1/2 power. So if you see a square root, it's the 1/2.
So keep those in mind. I think we're about to combine the two. If there's any justice. No, not yet. Let's do this one. Log base 64 of 2. So I want to do this one separately. Say it again. It is 1 over 8. Let's see why that is the case. So log base 64 of 2. I don't know what that is, right? So I'm going to call it x.
Okay. So if you can't read it off, well, we'll do it 2 ways. You got 1 over 8. You can get 1 over 8 because you know that 2 to the 8 is 64. So 64 to the 1 over 8 is 2. Right? If you can see that, that's fine. I want to show you a systematic way of doing this as well. Okay. So if you don't know what it is, call it x and we'll find out what x is, right? So we have that. What does this by definition mean? It means that what? 64 to the x equals 2 for sure. Okay. And now that we have these things written, we would like to get the same base. Right? So we're going to solve this by finding a common base. And we'll notice that both 2 and 64 can be written in terms of 2. Okay. So that, I think it's 6, not 8. I think it's 6. So that 264 is 2 to the 6. So you just find out how many 2's are in 64, right? And it's 6, so then 2 to the 6th to the x power is equal to 2. So now you're just changing the bases so that they match up. And once the bases are the same, then you can just make the powers the same. And we can solve for x. Okay.
Can you say what you said the first time?
That, wait, here?
Yeah.
Right, so here, if you don't know what it is, call it x, and then we use the definition. The definition says that if I have log base 64 of 2 is equal to x, then 64 to the x power is equal to 2. And that's how I get this step. It comes right from the definition. 64 to the x power equals 2. And then when you have this, the hope is hopefully these are the same base, or we can write them in terms of the same base, and 64 is 2 to the 6th, so I replace the 64 with 2 to the 6th power. Now what do I do with these two powers? What happens? They add or multiply. They multiply. So that 2 to the 6th all to the x power is just 2 to the 6x, and that equals 2. 2 to the 6x power equals 2 to the first. The bases are now equal. The only thing we can conclude is that 6x has to be 1. When the bases are the same, you have to make the powers the same. And now we can solve for x. Divide both sides by 6, x is 1 over 6. So when you have an exponential equation like this, one of the ways to solve it, if you're lucky, is that they both come from the same number. In this case, they do. It's 2, right? Both of them in terms of powers of 2. Do some simplification. Once the bases are equal, set the powers equal and solve. Divide both sides by 6. X is 1 over 6. Log base 2 of 2, 1. Log base 4 to the 7th, 7. 8 to log base 8 of 9, 9. Oh, like a choir in the church. The domain. Street version, I can only be taking the log of positive things. We said that the domain of the logarithm is 0 to infinity. Whatever's inside of a log better be positive, right? So that when I write log base, the domain of log base b of u is the u has to be greater than 0. And so when I see log base 6 of x plus 2, I'm just saying x plus 2 needs to be bigger than 0. I need to solve for that. Okay. I'll subtract 2 from both sides and I'll write this in integral notation.
Why does the u have to be greater than 0?
That's a great question. So there are a couple of ways to see it. But so suppose, we'll use the skeptic way first. Suppose I could make it negative, right? Suppose I had log base 3 of negative 5. What is wrong with that, right? Well, if that actually existed, of course I could call it x, right? And then what does this mean by definition? It means that 3 to the x equals
-5. Oh, that's just not possible, right? I can't have a power of 3 that's negative, right? And of course, this has nothing to do with 3, right? Any base that's positive, remember b has to be positive, you can't raise b to any power and get something negative. Right? You should never be taking logs of negative numbers. The other way to explain it is that, again, it's the inverse of the exponential. If the exponential never goes below the x-axis, the inverse can never go to the left of the y-axis. I can't put in negative numbers into the log. Thank you for your question. Right? So whenever you see logs, just remember the thing inside has to be bigger than 0. We subtract 2 on both sides. X needs to be bigger than -2. Interval notation. -2, and I want all the stuff bigger than that, not including that. -2 to infinity. All the stuff bigger.
Can we also put that in the calculator? Or
This one?
yeah.
Yes, you can. You might be able to, if you have a graphing calculator, you might be able to graph it and see where it exists, right? Your TI can't do a base other than the natural log or the common log, right? But if you went into Desmos and did log base 6 of x plus 2, you'll see that the vertical asymptote has just moved over 2 units. If I press home here, right, then it's here, right? -2 to infinity. That the graph simply does not exist over here. -2 to infinity. So that's a way of seeing it graphically. Log of 1 over 100. -2. Okay, if we can't see that immediately, then again you would just call it x. Log base 10 of 1 over 100 is x. By definition, 10 to the x is 1 over 100. And now we're in the space where we have to find a common base. What's the common base here? 10. Everything here is a power of 10. And so this is 10 to the x equals 1 over 10 to the second. 10 to the x, and here's where we need it. This is 10 to the -2. And so the bases are equal, so the powers have to be equal. So you just make everything a power of 10.
It's 10x equals 1 over 10 to the square. Is that in the inverse?
Say that again?
The inverse?
Here?
Yeah.
Yeah, that you do, it's the multiplicative inverse, that's right. When you have 1 over 10 squared, it's 10 to the -2, they're equal.
So if you have a fraction, it's always negative, right? Or
Yeah, when you have a fraction, it's always the negative of the denominator. Yeah. 10 to log base 10 to 23? 23. Natural log of e to the 5th? 5, right? So you just remember that this is base e, and they just cancel. So ln of e to the 5th is just log base e of e to the 5th. And again, they just cancel. E to the natural log of 111. 111. 16. Word problem. That function models the percentage of first-year college men in a certain country expressing anti-feminist views by agreeing with the statement X years after 1969. Complete parts A and B. Use the function to find the percentage of first-year college men expressing anti-feminist views in 2004. How much time is that? 35 years? Does this function overestimate or underestimate the percentage displayed by the graph, right? So they're asking you to plug in 35 into the function and compare it to the actual number and ask whether it's higher or lower. Right? And yeah, and just answer that, right? And then B. So let's just do it. So f of 35 is equal to negative 7.32, the natural log of 35 plus 64. Right. And then you would just check which one is min. Min are dark gray, right? So you're just comparing that to 36.6 to see which one is larger. If that one's larger, then it overestimates it. If it's smaller, then it underestimates. We do this all the time. Try and apply functions to real life situations.
Where did the equation come from?
Oh, they give it to us.
Oh,
That's the function.
37.97.
37 point, and the actual number is 36.6, so it would overestimate. And that goes in almost exactly in the TI. It looks exactly like that.
By how much does it differ? You would just subtract. Use the function to project the percentage of first-year collegemen who expressed anti-feminist views in 2010. How many years is that? Is that 41? 41 years, right? And then, yeah, you're just plugging in 41.
The loudness level of a sound D in decimals is given by that formula, 10 times log of 10 to the 12 times I, where I is the intensity of sound in watts per meter squared. Decibel levels range from 0, barely audible, to 160, a sound that is going to wreck your eardrum. The sound of a certain animal can be heard 500 miles away, reaching an intensity of 4.2 times 10 to the 4th watts per meter squared. Determine the decibel level of this sound. At close range, can the sound of this animal rupture the human eardrum? It seems like they've given us a ton of stuff. What is D here? D is decibel level. So say it again. Oh, that's what I'm saying something. Okay. So the decibel level of this animal's sound is approximately what? So what were you going to do? We're going to plug this in, right? Right, so
Yeah, so it's just going to be D equals 10 log of 10 to the 12th times 4.2 times 10 to the 4th, 10 log of 4.2 times 10 to the 16th.
And then you just see what that is. And then if that number is near 160, then you would say yes. If it's not, then you would say no. Say it again?
166.
166? So then you would mark yes.
All right, that is that homework. We'll break there
For 5 to 7 minutes, and then we'll do one more.